Friends, welcome back. So far we've gone from a 2D image here to a flattened 1D learnable embedding vector, or in VIT terms, a linear projection of flattened patches. But right now our code is a little bit all over the place. So let's turn it into a single PyTorch module, because that's our goal, right? We want to turn a paper from math, text, and figures into reusable code. So I'm going to make a little heading here. 4.5, turning the VIT patch embedding layer into a PyTorch module. So what we're doing here is we're slowly constructing layers and blocks, inputs and outputs, little Lego bricks that we can eventually put together and create the overall VIT architecture. So we want this to do a few things. We want this module to do a few things. 1, create a class. We'll call it the patch embedding class. Nice and simple. 2, we want it to initialize with appropriate hyperparameters, such as channels. We want embedding dimension and patch size. 3, what else do we want to do? Well, we want to create a layer to turn an image into embedded patches using Conv2D and Conv2D. You might want to go ahead and try this out yourself once we've got these steps, by the way. So you can pause the video, and then we want to create a layer to flatten the feature maps of the output of the layer in step 3, so the flatten layer. And then 5, we want to define a forward method, because if we're creating a PyTorch module, this is going to, that inherits from nn.module. Recall that we've made a few of these now. All PyTorch subclasses, or all classes that subclass nn.module, should have a forward method that defines the forward computation. So we want it to, e.g., pass through layer from 3 and 4. And then finally, 6, we want to make sure the output shape of the layer reflects the required output shape of the patch embedding. We want to make sure our shapes line up, right? Because that's one of the biggest issues in machine learning and deep learning, is mismatched tensor shapes. So there's a few steps here, and my challenge to you is to pause the video now and give this a go. And I have some advice for you. It's from one of my favorite people. Oh, well, before we get into it, I'll just show you what we want our layer to do. So this is our original image input. We might come and rewatch this movie again. So original image, this is what we want it to do. Cut it into patches using the Conv2D layer. Now we've done this by hand so far. There we go, Conv2D. Then we want to set the kernel size equal to the patch size, so we can create a patch here. Then we set the stride equal to the patch size as well. So our kernel steps over patch size steps each time. Now this is only 9 patches, but our image is going to use more than that. Then we're going to flatten it into a sequence using a flatten layer. And then these steps will come later on, but these are the first steps that we want to focus with the module that we're building now. And so this is Lao Tensor, one of my favorite people in the world of machine learning lore. You can see he loves machine learning. He's got PyTorch and TensorFlow symbols there. Just remember, creation of a deep neural network starts with the first layer. So that's a wise quote from Lao Tensor, and that's what we're doing here. We're rebuilding VIT, and this is starting with the first layer. So give that a shot, and I'm going to continue the video in 3, 2, 1. How'd you go? Did you create the patch embedding layer? I hope you gave it a shot. Otherwise, let's do it together, hey? So I'm going to start off by creating a class and call it patch embedding. So this is step 1. Step 1, create a class called patch embedding. And we want the input and output of this layer or class or PyTorch module to be, oh, not patching embedding, I want it to be patch embedding. To be an image and the output to be something like this. So let's see if we can do that, hey? Then we need to initialize our layer. So this is step 2. Initialize the layer with appropriate hyperparameters. Now we're going to construct this in a way so because we're focusing on replicating VIT base to begin with, we're going to construct our layers though in a way that if we wanted to add more parameters later on, we could do that. So we can do that by setting this in channels. We'll give it a type hint to be int. Out channels, we don't actually need that. That'll be the embedding size, won't it? So the patch size, we want that to be 16 by default. And then the embedding dimension, which will be the out channels of our conv2d layer, is going to be 768. This is from table 1 for VIT base. So you see later on, if we wanted to create this class, an instance of this class, we could update the embedding dimension there if we wanted to, and also the patch size. So let's keep going. We'll call super.init. Wonderful. And now we have to start setting up our layers. So we need to create a layer to turn an image into embedded patches. Embedding patches, embedded patches. We've got typos galore through here, but we're not here to learn how to type properly. So step 3 is to create a layer to turn an image into embedded patches. So let's call this self.patcher for the patching layer. And we'll use nn.com2d. So just exactly the same steps that we did above. We just need a layer that's going to replicate this. So we have in channels is 3, out channels is the embedding size, and the kernel size is equal to the patch size, and the stride size is also equal to the patch size. So we'll come back down here. So I'll set the in channels equal to in channels, because that's going to be this parameter up here. And then the out channels, what will that be? The out channels will be the embedding dimension. Embedding dimension. Then we can set the kernel size is going to be equal to the patch size. The stride is equal to the patch size. Look at us go, we're on a roll. And then the padding is equal to 0. We don't need any padding here. Beautiful. So let's keep going. Number 4 is to create a layer to flatten the feature maps of the output of this. So we just want to replicate what we've got here. Nice and simple flatten layer to flatten the feature map dimensions of the output of our convolutional layer. So just like we did in the step above. So that's going to flatten our patch embeddings into a sequence. So create a layer to flatten feature map outputs of conv2d. Self.flatten equals nn.flatten, and the start dimension is going to be dimension 2, and the end dimension is going to be dimension 3. Beautiful. Now what are we up to? So we've got to define a forward method. Look at us go. We're creating the patch embedding. I mean, that took us a while to create it, but now we're just replicating the whole thing. After we've been through it step by step, we're doing the whole thing in a few lines of code here. So forward, I'm going to take self. I'm going to just write a little note here. Number 5 is define a forward method to define the forward computation steps. Not the most ideal comment, but we get what's going on. So the input here is going to be our input image, and we want it to go through the patch embedding first. But we also want to get the image resolution. Let's get a little check here, hey? We'll make an assertion, because we want to make sure that the image resolution is compatible with the patch size. To check that inputs are the correct shape. So we can go image resolution equals x.shape, and we'll get the last dimension. And then we'll create an assertion here. So we want to assert that the image resolution is divisible by the patch size and that there's nothing left over. And so if it's not, let's go input image size must be divisible by patch size. And the image shape we'll put in here, image resolution, and then we'll go patch size is equal to self.patch size. Beautiful. I think that should work. If not, we'll find out, won't we? Let's now perform the forward pass. So if our input image passes the assertion, we want to now pass it through the patch embedding. So we'll set it to x patched equals self.patcher on the input. And then we can pass it through x, we'll call it x flattened, and pass it through the flatten layer, self.flatten, and we'll pass the patched embedding through there. Wonderful. And now finally, we want to recall that the output of this is not going to be in the right order of dimensions. So we originally had, the embedding dimension as dimension 1, but we want the number of patches as dimension 1. So we can call a permute, just like we've done here, to rearrange it to be batch size, number of patches, embedding dimension, right at the end. So that's step 6. Make sure the returned sequence embedding dimensions are in the right order. So we want batch size, number of patches, and then embedding dimension on the end. Return, we want x flattened, and we're going to permute. We want to change, keep 0 where it is, so keep the batch size where it is, then we want 2, 1. Now, is that correct? Well, we're going to find out, aren't we? So how do we test this? We're going to pass an image through, and we can also test our assertion as well, right? So let's call our setSeeds function, because whenever we instantiate a layer, it's going to instantiate with random weights. So if we instantiate an instance of this, just to try and make sure you're seeing what I'm seeing, we'll set the seeds, and actually we're probably going to see something different, because unless your image is the same as mine, we're going to get different results. So let's go create an instance of patch embedding layer. So we're mostly interested in seeing the shapes are correct here. Patch embedding, this is just what we've got above. So we don't actually need to insert any parameters here because the defaults are going to work for us. But why don't we do that for completeness? Patch size equals 16. So this is where you can see that if we wanted to change the patch size, we could. And if we wanted to change the embedding dimension to something else, we also could do that. And so let's go pass a single image through patch embedding layer. So let's go print, we'll go input image size, go image.unsqueeze 0.shape, and then we'll go patch embedded image equals patchify. So this is our layer that we just created here. And then we'll pass through image.unsqueeze, add a batch dimension. So here, add an extra batch dimension. We did the same thing here as well, actually. And what is Colab telling me? Oh, I need to finish the F string here. Did you catch that? And then finally, let's print the output shape. Output shape. This is actually a sequence or a patch embedding sequence shape. A lot of manipulation here, but that's all right. Nothing we can't handle. Patch embedded image. Do we have the right shape? 3, 2, 1. Let's go. No errors. Yes! We did it. We've got a single layer here that now turns our single image into a patch embedding or a sequence of patch embeddings. Look at that. We start with the image 1, 3, 2, 2, 4, 2, 2, 4, and we end with 1 number of patches embedding dimension, which is exactly what we wanted. If we come right back up here where we calculated the input and output shapes by hand, oh my gosh, we've written a lot of code. Here we go. Input shape. Well, our color channels is at a different point, but that's okay. And then we've got here the output shape, single 1D sequence of patches. Well done. We've got our first layer of the VIT. So what's next? We could reuse this whatever we want. Patch embedding. What should we do next? Well, we've got the main part of equation 1 done, right? So equation 1, the patch embedding. Now I've just altered figure 1 a little bit just to focus on the linear projection of flattened patches. This is what we've replicated. We've gone from a 2D image into a sequence of flattened 2D patches. So we split an image into fixed size patches, linearly embed all of them. So that's what we've done. We've created these linear projection of flattened patches. We've made this portion of equation 1. So if we keep going, this is what we've replicated so far, one layer at a time, patches and map to D dimensions with a trainable linear projection. So D dimensions is our embedding dimension. So if we use an embedding size of 768, and an image size of 224, 2243, we've now got number of patches 196 with an embedding size of 768. And this is going from this shape to this shape, which is this shape, height, width, color channels, to number of patches times patch size squared dot color channels. So that's a huge effort. And to see it in code, well, this is what we've done. So now we've done probably the largest portion of the patch embedding. We still have the class token and the positional embedding. So you might want to think about how you could do that on your own. So we need to create this little class token here and these position embeddings. But we're going to start to do that together over the next few videos. So equation 1, the class token. Let's come and check this out in the next video. I'll see you there.